towards a low-cost Wi-Fi based real-time human activity recognition system. Our research project is the Wi-Fi CSI based real-time human activity recognition using Raspberry Pi. In the modern era, due to our busy lifestyles, human monitoring systems for the elderly have become important. Current state-of-the-art solutions are mostly either video-audio based or require wearable. In an increasingly privacy-conscious world, video-audio based solutions can be considered a privacy risk. In the past decade or two, the access to Wi-Fi and the use of smartphones in general households have greatly increased. The working principle of the recognition of activities of daily living using Wi-Fi is the changes in the Wi-Fi signal over time when the signal gets reflected off of and absorbed by the human body. We can use Wi-Fi for human activity recognition due to multipath propagation. The change of position of objects within the environment will cause changes to the signal. The channel state information of data packets lets us retrieve the amplitudes of the OFDM subcarriers. We will be using the variations in the amplitude of these subcarrier signals to recognize human activities. There is a need for an alternative to the currently available human monitoring systems. This is a field where active research is being done. Most of the available systems have drawbacks. Audio and video based solutions require direct line of sight, require a certain amount of light and have privacy concerns. Wearable based solutions are inconvenient. They are difficult to wear constantly and have to be regularly charged. Depth sensor based solutions also require line of sight, so multiple sensors are required which can be inconvenient. Current Wi-Fi based solutions are mostly implemented on network interface cards that are embedded in larger devices such as laptops. Therefore, they are expensive and have a high power draw. Therefore, there is a need for a small, inexpensive, low-powered Wi-Fi based solution for human activity recognition. Our motivation in our project is to address these shortcomings of existing solutions. Privacy-related concerns will be reduced as no audio, video, or spatial data is being used. The system will allow for real-time recognition of human activities. The primary objective of the research is to develop a monitoring system that can detect and recognize human activities of daily living. Our objectives are to develop a public dataset of CSI data of several activities, a deep learning model to classify Wi-Fi CSI data to identify those activities, and the application to recognize human activities, which includes the server-side application which will recognize the activities and the Android app that will notify the user. Next, we'll look at the methodology and the implementation. This is a high-level architecture of the overall system. A Raspberry Pi 3B Plus will act as a Wi-Fi access point. Another Raspberry Pi 3B Plus will capture packets, process them to extract the CSI amplitudes and then upload them to the server-side application. The server-side application will then send it through the deep learning workflow and send notifications to the mobile app. We are using two Raspberry Pi 3B Plus devices. One Raspberry Pi was set up to act as a 5 GHz Wi-Fi access point. On the other Raspberry Pi, the CMON Nexmon CSI library was set up to capture CSI data. These are the test environments used for the experiments. They were performed in two average-sized bedrooms. The test was conducted by 4 subjects. The figures show roughly where each activity was performed. Both Raspberry Pi devices were placed at a similar height from the ground in both test environments. 6 activities were performed, namely standing up, sitting down, getting into bed, walking, falling, and no movement. Each subject performed the activities 30 times, resulting in a total of 120 data points per activity and a total of 720 data points in the entire dataset. Data was captured for 10 seconds for all the activities. The sampling rate of the Wi-Fi access point was set to 50 Hz. Therefore, each data point is comprised of 500 packets. The Raspberry Pi was connected over Ethernet to a Wi-Fi router. The data captured was controlled by the subject using a separate device connected to the Raspberry Pi over SSH through Wi-Fi by connecting to the previously mentioned Wi-Fi router. We used a convolutional LSTM model for the recognition of activities. The model consists of two convolutional 1D layers, a max pooling layer, 4 bidirectional LSTM layers and a dense layer. The model was fed with the data we captured as batches of 100 sets. There were 720 data points in the training dataset, where each data point is a 500 by 234 matrix. Each convolutional layer used for the model has 128 filters with a kernel size of 5. Bidirectional LSTM layers with 200 units were used. Finally, the model classifies the data points into 6 activities we mentioned earlier as the output. Next, we will look at the experimental evaluation of the system. These test results are for the convolutional LSTM model detailed previously. Of the 120 data points for each activity, 100 were used for training while 20 were used for testing. We managed to achieve a dataset accuracy of 95%. The confusion matrix for the different activities are also given here. The accuracy of stand up, falling and getting to bed are very high, while the other activities have accuracies ranging from 92 to 95%. Next, we will look at the real-time setup. We configured a Raspberry Pi 3B Plus to work as a 5 GHz Wi-Fi access point using host APD. The packets are generated at a rate of 50 Hz. We configured another Raspberry Pi 3B Plus to capture CSI data using the Nextmon CSI library. A client application running on the Raspberry Pi captures packets and extracts the CSI amplitude data in real time. It then uploads the CSI packets to a server-side application. We have built a native Android app that shows notifications when activities are detected. The app will work as an MQTT client. When the backend server detects an activity, it sends the data to the MQTT server. Then the MQTT server will notify the client implemented on the app. The user needs to connect to the MQTT server to receive the data from the server by pressing the connect button. The app will be run in the background to receive data and to send notifications. If the app receives the same activity notification in real time, it won't show it until the activity changes to a new activity. There are two notification types in the app. They are no movement alert and falling alert. An alert for no movement will be sent to the user when the server detects no movement for a long period of time. An alert for falling will be sent to the user when the server detects the falling activity. Users can find activity history by pressing the floating button on the home screen. The activity data will be presented to the user by fetching the data from the server. Activity name, probability, date and time will be displayed to the user for each activity. The following tests were done in test environment 1. The test environment was stationary and additional data was captured to retrain the model, bringing the total size of the dataset to 840 data points. The accuracy of no movement, stand up and sit down ranged from 65 to 80%, while getting to bed and walking activities had a very low accuracy. We have created a dataset of 840 data points of activity data. We have built and trained a convolutional LSTM model to classify activities. We have achieved a dataset accuracy of 95%. We have achieved reasonable real-time accuracy for certain activities in a static environment. Real-time implementation requires further work, either in the form of a significantly larger dataset or a different approach altogether. The research outputs are the dataset of human activities, the convolutional LSTM model for activity recognition, the client application for real-time data capture, the server-side application for processing, and the mobile application to view activity predictions and receive notifications. Next, we will look at a real-time demo of the activity recognition system. Thank you.